Hello all, welcome to this interesting video session on Kepler's first and the third law. So today we are trying to describe what are the Kepler's laws. So we have in fact the second law which is in place. So probably in the next video I'll try to cover what is Kepler's second law. So today we'll try to cover Kepler's first and the third law. The first law is basically called as the law of periods. Okay, so the first law. So we have the first law and we have the third law, okay? And the first law is called as the law of orbits, and third law is called as the law of periods. Okay, so which deals with the time period equations. Okay. So law of orbits, which really states that for any planetary motion, okay, if a planet is revolving around the sun which is placed at the foci of any ellipse, then probably the revolving path which is being covered by the planet, it is basically the ellipse. Okay, so that is what it is trying to convey. So basically we if we have a ellipse profile, if you draw like this, okay, if you draw a profile like this, okay, now we have an ellipse. Okay, so while practicing you can draw it very neatly. So now I am just drawing a little bit of rough because I'm not that much good in drawing. So these are the vertex of the ellipse. Okay, so this is the center of the ellipse. Let's say we have a C. Now let's name these vertex A and B. Okay. Now the sun is located at at the foci distance. So this is the foci distance. So if here also we have foci. So here also we have the vertex. So this is one foci where sun is being placed. So let's say we have sun here, and I take a planet of mass m. So it can be any planet. So it's a planet, so which has been revolving around the sun in an elliptical orbit, and where sun is kept up the foci. So that is called the law of orbits. So law of orbits we have explained because for any planetary motion, it exhibits an elliptical path around the sun, which is placed at the any of the foci of the ellipse. Okay, any of the foci of the so sun can be here also. Okay, so it depends where sun is being located. So as per Kepler's, he just noticed that the planets are revolving around the sun when it is kept at one of the foci of the ellipse, and it exhibits an elliptical path ultimately. Okay, so that is what your Keplerian law of period states. So when it comes to law of periods, again the things are much more complicated. So we'll try to make it things more simpler, and that is why we are here. So probably now let's say the position of the sun is here. Okay, now I take a distance from, now I take a point, or I name a point, okay, it should be clear. So we have D point here, okay. Now let's say we have a D point. So from D to B, okay, we define a distance called the aphelion. It's called the RA, okay, up to this point, okay, up to this vertex point, okay. So when planet reaches to here, so this is the maximum distance the planet and the sun is at. Okay, so that distance is called the aphelion. And according to the ellipse dimensions, when we want to have the dimensions of the ellipse, okay, we have the total axis is going to be the major axis. Okay, now we'll just describe only the major axis. Now let's say this is 2a. Okay, now this is 2a. This is 2a. Okay, now again, so the distance from center to the foci, okay, now sun is located at the center, okay, sun is at the center, so the distance from the center to the foci distance, so that is called as a into e. Okay, a into e for an ellipse. If you have studied your ellipse, your conic sections in your elementary classes, so please go and have a look. So we have, there are different dimensions of ellipse which we have mentioned. okay, where E is the eccentricity. So eccentricity is, by physical, it means how much deviation from a circular profile, that is called the eccentricity. Okay, so definitely if any motion it is not circular, then probably we have to associate a parameter which is called the eccentricity. So ellipse anyway it is not a circular path, so eccentricity comes into picture because it is basically the deviation. Okay, so basically it deviates from 0 to 1 for an ellipse. So simply for parabolic profile we have different eccentricity values. Okay, so for hyperbola it is again greater than 1, so parabola it is equal to 1. So if it is ellipse it should lies from 0 to 1, so it keep going. So probably you can uh, take some time and try to recollect whatever concepts you have learned. So it's up to your interest whether you have to recollect or not. But here I'll just tell you, this is the center point. From the focus point we have A. Okay, now we need to remember one thing. We have the total distance, here it is A. Okay, now let's say we have the total distance is going to be A. If this is 2A, from here to here it is A, so it should be geometrically this should be equal to A. Okay, so my drawing is not that good, but probably you can just correct yourself. So this is from A to C it's A, C to B it's A, so ultimately it makes 2A. So A to C is again the semi major axis, C to B is the semi major axis. Okay, so this is A here. Okay, so now you can explain what is an aphelion radius or aphelion distance, which is equal to your A plus A. So which is again A into 1 plus E, which is equal to the aphelion distance. So always you remember your aphelion distance is very great, much greater than your radius of the sun. Okay, because here I am not taking the radius of the sun in the center. So if you are taking the center, you have to consider the radius of the sun, which you have done previously for taking the radius of the earth. Okay, when we derive the orbital speed and those stuff. So here I am not taking the radius of the sun because your aphelion distance is very much greater than your radius of the sun. I think this concept is clear. Okay, so that is the reason we are not taking the radius of the sun. So when planets comes to this position, then this is the aphelion position. Similarly, when planet comes to this position, so then probably we have another term which is called as the, so we have another term which is called as the R of P. This is called the perihelion distance, which is called as the RP. So RP is equal to, so this total is completely, this A to C is A, so this is AE, so this distance will be the total minus this one, so A minus of AE, so it should come around A into 1 minus of E, which is a bit clear from the geometry. Okay, I hope this is clear for you. Okay, now again your RP, and always you should remember your aphelion and your perihelion is always having a very high value compared to your radius of any planets. Okay, including the sun itself. So it's very high. So that is the reason we are neglecting some of the radius of sun actually. Okay, some of the radius of bigger celestial bodies. So here it is the sun, so we don't take the radius as much, but instead we are more interested with the radius of the planetary motion, how it is close to the sun and how it is farther away from the sun. Okay, I hope this is clear. Now we are going to deal about the mathematical expression for the law of periods. Okay, now let's say I'll draw one more ellipse roughly, so that we need to construct some geometry. So this is my ellipse here. Okay, so this is my ellipse. Okay, now I construct an ellipse. This is my ellipse. So probably your sun is at this distance. Okay, it's very big. So now your planet motion is coming from this position to this position. Okay, now I draw a line like this here. Okay, and now I draw a perpendicular line so that it will make this curve little bit easy for doing some relevant uh, math, do some relevant calculations so that you won't get any complex terms. So I just draw a perpendicular line, okay, like maybe a tangent. So this will have a 90-degree angle. Now this is going to have a d theta component. Okay, Now this total distance is a into 1 plus e. This is the farthest distance away from the sun to the planet. Okay. So this is the distance traveled dx. So this is dx. Maybe the time taken to reach from here to here, let it be dt. Okay. Now this is d theta. Now from the geometry, it's very important. Okay. It's very important that your dx. Okay. Now you can write your dx divided by a into 1 plus e should be equal to tan of d theta. Okay. This is opposite side divided by the adjacent side. Okay, to the base opposite to the base of the right triangle. Okay. So that should give me like ax dx divided by a into 1 plus e. Okay. Fine, perfectly all right. If it is taking, if it is a cot theta also, it's okay. You take the trigonometric functions accordingly. Okay. Now we have, now if you are having a still geometrical confusion, you can do like this also. This is dx, this is a into 1 plus e. So basically you go with dx by 1 plus e. If this is d theta, then probably you'll end up with this equation. So if d theta is very small, and now let's say this is going to make a very, very small angle. Okay. So then tan d theta is again tending to d theta. Okay. So tan d theta is very much tending to d theta for very small values of d theta. Okay. Very small value of d theta. I hope this is okay. Excuse me. So we have dx by a into 1 plus c. This should be equal to tan d theta, and dx by a into 1 plus of e, and that should give me a into theta. Okay, a into d theta. Okay. Now dx can be written. The total position is a into, now let's say we have d theta. Okay. Now a into 1 plus e times d theta. Now you differentiate with respect to time dt because it is happening at a very small values of dt. So now I divide the LHS and the RHS term by dt. So you get dx by dt is nothing but the orbital speed. Okay. So again, the orbital speed that should be equal to a into 1 plus e into d theta by dt is omega. So you have seen d theta by dt is the angular displacement. Okay. Angular displacement upon t. So angular velocity we can call, this is also called as the angular frequency. Okay. Accordingly, so we have different terms. If you see sine waves and cosine waves, you are associated with some angular frequency, but it is happening at certain intervals of time. So here also we are associated with some intervals of time. So we have the t orbital time. So d theta by dt is again equal to angular velocity. So again your omega, if you have learned, your omega is always equal to 2 pi divided by t, which you have already learned. Okay. In your basic elementary physics chapters, 2 pi by t is the relationship between the time period and the angular frequency. Okay. Now in our previous classes, we have already have an expression like v orbital. So conceptually we'll go. Okay. Conceptually, if you go, we have root of mu divided by, when it comes to denominator, you always take the distance of separation between the two bodies. Here the distance of separation is Ra. So my total distance will be from this planet to this planet. So that is basically Ra, which is a final position. So your Ra is equal to a into 1 plus e. So I substitute the same here. Okay, this is what ultimately we retrieve the concepts here, because ultimately it basically denotes the separation distance. Okay, how much it is been separated. So this will happen at the apoapsis, that is called the aphelion. If it is in the perihelion, then the story will change. It will be 1 in a into 1 minus of e. So I think these concepts are pretty clear. Now we equate the two equations. So here I can write a into 1 plus e omega, which is equal to, I'll split the roots so that it will be clear for you. Root of mu times root of a into 1 plus e. Okay. Now omega, you know, it is basically 2 pi by t. So you substitute accordingly, 2 pi a divided by t. Here it is t orbital time. okay, into 1 plus of E, and that should give me again this expression, okay, again this expression. Fine. So we'll write it neatly again. So we have 2 pi a divided by t orbital into 1 plus of e, that should be equal to root of mu, which is a gravitational parameter, under root of a into 1 plus e. Okay. Now you do the cross multiplication and other math stuff. So t orbital, that should yield me. So if I take this t orbital this side, this root mu should come here, and I'll take this gentleman here. So you get 2 pi into a to the power of 3 by 2 into, okay, 1 plus e to the power of again 3 by 2, because root a is a half into a is a 3 by 2. Root of 1 plus e is 1 plus e to the power of half into 1 plus e. So this is 1 plus e to the power of 3 by 2. This is a basic math again. So divide by root of mu. Okay. Now if I take, so here my favorite planet is Venus, because in 2025 we have a space mission which is coming up. So that is called the Shukrayan program. So that will be headed by ISRO. So I dedicate this E value for, at the time being, we have a Sun and the Venus combination. So probably your E value is going to be, if for this particular Earth, when Venus is there, when Sun is there, okay. So your E value is going to be 0.00, let's say 67, okay, which is very less, okay. Now, if you substitute here, you're going to get a very low value. Okay, so this term will vanish off. So similarly, for other planets, your E value basically lies from maybe my 10 power minus 3 to 10 power minus 2. So it depends upon the planetary profiles. Okay, so for all the elliptical profiles. So again, this is a constant. 1 plus E is again a constant. Root of this portion is also again a constant. Again, 2 pi is also again a constant. So ultimately, we end up. So we cannot take everything as a constant, but because we are more interested with a to power of 3 by 2. Okay, maybe with experimental data result, we can tell me, okay, your a values keeps changing. Okay, so we take t orbital, and that should give me something called a to the power of 3 by 2. Okay, this is the expression in terms of the semi-major axis, which can be also written as t square proportional to a to the power of 3. Okay, that means the square of the time period is directly proportional to the cube root of the semi-major axis of the elliptical path for this particular planetary motion. So that describes the law of periods. I think we have satisfied the law of periods condition here. Again, this is a proof for law of periods for elliptical path. And for a circular path, we have seen t square is proportional to re to the power of 3. Okay. So I think these two equations are very well important. So I think we have successfully completed the derivation for this equation, and now again t orbital is probably we can write in a standard way. This is 3 by 2 or something. Okay. Now I'll just mark it here. So this is basically called your law of periods. Okay. So this is called law of periods. Well, this is explained in Kepler's famous book called the Book of Harmonies, which he was published around 1500 year. So probably this is one of his greatest contributions. So the basic practical approach how astronomers are using is like when we have a planets. Okay, now let's say we have a time period of one planet and we have a time period of other planet. Okay, and we know the position of one planet and we don't know what is the position of the second planet, then probably we can find out accordingly, basically with this equation. And similarly, if we don't know the planetary time period or the time orbital time period of the second planet, then probably you can go with the similar equation if you know the two position where it is located. So these all things will happen only because of the law of periods, which was proposed by Johannes Kepler, and this is a very useful work. And we have also seen law of orbits where planets revolve around the sun in elliptical orbit, and sun is kept at any one of the foci of the elliptical path. So here is a foci. So this is a foci distance from center to this position. Okay, so this can be here also. This is also can be considered one of the foci distance. So it's up to you how you make the stuff to understand. So I think this feels me very interesting for me. Okay, so when you take the sun and the earth combination, okay, when you have sun and the earth profile, your eccentricity value, now let's say this is my earth and this is my sun, your eccentricity value is probably going to be 0.0167. Okay, and this is for the sun and the earth elliptical profiles. Okay, and similarly, we obtain for other planets according to the data book, which you can get it from the internet or any sort of your study materials recommended by your universities. Okay, so I think we have successfully completed. Hope you have enjoyed this video, and let me know of any suggestions so that we can add some more videos onto it. And I request you all should practice this and you come up with some good result. Okay, so thank you so much.